The goal for this tutorial is not only to cover AWS VPC, different types of subnets you might have, network components such as internet and NAT gateway, and of course we'll go over route tables, what they are, what it means to have a default route, and more. But since it's also a Terraform tutorial, in the first section we'll focus on AWS and pretty much declare all those components as is in Terraform. In the second part, we'll focus on how to optimize Terraform code. For example, I'll show you a couple of ways to create multiple resources of the same type without the need to copy and paste and use count instead. This is the same approach that Terraform AWS module uses and has few drawbacks. Next, I'll show you a more flexible approach of using a map instead of array and using for each loop that allows you to iterate over each object in the map and use keys and values. Also, sometimes you want to have conditional variables, like creating certain resources only when you need them. And I'll show you how to use them with a count variable. Finally, some Terraform resources have repeated blocks, like security group inbound rules. For that, we can still iterate over the map, but with a slightly different approach. Before you can start using your VPC, you need to create a subnet. When you create your AWS account for the first time, AWS automatically generates a default VPC for you, which you should only use for testing purposes. Let's say we want to deploy a web server like Nginx for applications that need to be directly exposed to the internet. We want to create a public subnet. Additionally, we need to create internet gateway and attach it to our VPC. Now, if our web server has a public IP address, it can access internet. For example, to download packages to install software like Nginx itself. And that virtual machine will be directly accessible from the internet via its public IP address. However, we need to manually associate internet gateway with a subnet. For that, we need to create a route table. Whenever you create a VPC, you automatically get a route table with a route that allows your virtual machines to communicate with each other. This route covers your VPC's seeder block, meaning if one virtual machine wants to send a request to another within your VPC, it will use this specific route. To reach the internet, we need to create a default route. A default route simply covers cases where the target IP address is outside your VPC seeder block. So we now have a VPC route and a default route. If a virtual machine wants to send a request to another VM inside the VPC, it will use the VPC route. If the target IP address is outside of the VPC, it will use default route and send the request to that target IP via internet gateway. In practice, public subnets are mostly used by load balancers. You typically deploy your VMs to private subnets and expose them to the internet using a load balancer in the public subnet. Most of the time, we want internet access as before to download packages or perhaps access external APIs. However, we don't want to directly expose those VMs to the internet for security reasons. For this, we can create a NAT gateway. If a VM with a private IP address needs to access external service on the internet, the request will go through the NAT gateway. The VM's private IP address will be linked to the NAT gateway's public IP address, allowing the VM to reach internet using a public IP. All other VMs in that subnet will share the same public IP. This is static public IP address that you can whitelist with your clients if needed. To create a private subnet, we need to create another route table with a default route to NAT gateway and associate it with a private subnet. The logic is the same as with default subnets. If the target IP is outside your VPC, the request will be routed using a NAT gateway. Private subnets are likely the most commonly used subnet type because they provide internet access while isolating VMs from direct internet exposure. For example, Kubernetes nodes would almost always be located in private subnet along with ECS nodes, with only load balancer in the public subnets. In some cases, you want to ensure that your applications, most commonly databases, are secure and have no outgoing or incoming access to the internet. For this, you can create isolated subnets. These subnets do not have any default routes, as seen previously, only a VPC route, so they are completely isolated from the internet. This setup is more secure, but to install anything, you need to use internal services or host your artifacts in the S3 bucket. For example, isolated subnets are rare and more secure, but they require more infrastructure in general if you decide to completely isolate everything from the outside world. Let's go ahead and create a folder where we will keep our Terraform files. First, we need to declare AWS provider. In the previous lesson, I explained how to create IAM roles for Terraform and properly authenticate with AWS. For simplicity, I'll use default approach. Next, let's set version constraints on the Terraform and providers. The next step is to create a VPC. We have a resource name that you can always Google to find all available configuration options. We also need to assign it a variable, in this case main. One of the most important parameters is the seeder block. You need to pick a large enough range that does not conflict with other networks you might have if you want to peer multiple VPCs or join on-premises networks with your AWS account. The next options are important for the future because many components rely on DNS, so let's enable DNS support from the get-go. Additionally, we can attach some tags. For example, we can use a special name tag that starts with a capital N, which is visible by default in AWS console. That's all for the VPC resource. Next, we need to create Internet Gateway and attach it to the VPC we just created. Also, we can give it a tag. A common naming convention is to use environment prefix in your naming, as shown here. This makes it easier to differentiate environments like staging, development, and production in a single account. Next, we have public subnets. They are mostly used to create load balancers and serve as entry points to your infrastructure. We'll start by creating individual subnets and then automate in the second part of this tutorial using count and for each loops. The most important parameter is also a seeder block. You can use one of many online calculators to divide your main VPC seeder into multiple subnets. We also need to create subnets in different availability zones. This not only increases availability, but is also a hard requirement for some services like EKS. Optionally, we can enable AWS to automatically assign a public IP to any EC2 instance you create in this subnet. It's optional and you can disable it if you want. In this case, tags perform more functions than just showing up in the UI. First, we have a name tag using pattern of environment, name, and availability zone. Next, we have a tag that you should only use if you plan to deploy EKS. This tag is used by EKS service to discover public subnets to provision public load balancers. The next tag is also for the EKS service, so you can omit both if you're not planning to use Kubernetes. Here, dev demo is the EKS cluster name. Alright, next let's create a second public subnet that has a different seeder range and availability zone. Again, for the seeder, you can plug in your previous range, find the last IP address and use it for this subnet. At this point, we have two public subnets, but they're not actually public since they do not have routes associated with the Internet Gateway. Let's go ahead and create the route. First, let's create a public route. It will have a default route to the Internet Gateway. We can give it a tag as well. Next, we need to associate public routes with the public subnets. It's very straightforward. So now we have public subnets and any EC2 instance created in those subnets can reach any resource on the internet. Next, we need to create a NAT gateway that converts private IP addresses of the VMs to public ones to allow internet access for private subnets. First, we need to allocate a public IP address and use it to create a NAT gateway. You can provide this IP address to your clients in case you need to whitelist it. Next, let's go ahead and create a NAT gateway. Usually, you have a single NAT gateway that you need to place in one of the public subnets. We also need to explicitly depend on the internet gateway. Now, since we have a NAT, we can start defining private subnets. It's very similar to public subnets. You need to use a seeder range and place it in one of the availability zones. Then we have a standard name tag, and if you want to use EKS, we need to create a few additional tags. The first one will be used by EKS to discover subnets for creating private load balancers. The second one indicates whether the entire subnet is used only by EKS or can be shared with other services. Next, let's create a second private subnet in different availability zone. It might look like a lot of copy-pasting, but we'll fix it in the second section of this tutorial. Additional step is to create a private route table with a default route to a NAT gateway instead of internet gateway as in the public table. Finally, associate the table with the two private subnets. So now we have finally two public subnets and two private subnets. Sometimes you need a third type of subnet that is completely isolated from the internet. Frequently, those subnets are used for databases and services that need to be kept secure. So we'll create those two subnets and use default VPC route that allows VMs to only reach other VMs and services inside your VPC. Alright, let's go ahead and initialize Terraform. Finally, apply configuration. Let's quickly check if we have all those components in AWS. So first, we have our VPC. We have 6 subnets. For example, the public subnets have a default route to internet gateway. Private subnets have a default route to a NAT gateway. And finally, isolated subnets do not have any default routes, only routes within the VPC. Under route table, we have the public, private, and default VPC tables. We also have internet gateway. We have elastic public IP address for the NAT gateway. We also have a NAT gateway. Now, before continuing and optimizing Terraform, let's destroy it. Let's create another Terraform folder for the optimized version of the code. In this case, I'll show you different approaches to refactoring Terraform. First, let's go ahead and create local variables. I'll cover Terraform modules and best practices in the next tutorial. For now, let's use common sense and refactor some variables to avoid copy-pasting. Obviously, we need a region for the AWS provider. Now, let's copy and paste AWS provider from the previous section. Next, let's use a local variable instead of hardcoding a region inside the provider. Then, let's create a VPC seeder variable with the same value as in the previous part. Another commonly used variable is the environment, which is especially useful when you host multiple environments such as dev, staging, and production in a single account. Next, let's copy and paste VPC file. Let's replace VPC seeder with a local variable. We can also refactor the name tag and use environment variable instead. Let's refactor step by step and verify that everything is in place. Let's apply what we already have. Alright, it still works and we have created a VPC. Next, let me show you the first approach to creating multiple resources of the same type, like subnets. Let's create an array of availability zones and array of seeder ranges that we'll use for the public subnets. Copy and paste Internet Gateway file. In this file, we only need to refactor name tag. Next, copy and paste public subnets. This time, we don't need two resources. We can use a single one. Let's also make the resource variable more generic, so it can be used for multiple subnets. The first approach is to use a count variable, which is the same approach used in AWS VPC module. We create as many subnets as there are items in the array. Since we have two seeder blocks, we get two subnets. Now we need to dynamically assign a seeder to each subnet using index from the array. Similarly, we need to apply the same approach to the availability zones using count as index in the array. Let's also refactor some tags and use count as an index for the availability zone. You can apply the same strategy to other properties, like subnet tags, but I'll leave it as is for now. Next, we need to create route tables. We'll keep the table itself as is and just update the name tag. We also don't need two resources to associate public subnets with the route table. We can use a count instead. Update the variable to be more generic. Let's iterate over all public subnets in the array and use the index to associate this route table. That's pretty much all for the public subnets. You can see we don't need to copy and paste the same resources anymore, which makes the code more reusable and flexible if you need to create additional public subnets or use different availability zones. Let's go ahead and verify that it still works. We now have two public subnets with a default route to Internet Gateway. We also have the route table itself. For private subnets, we need to copy and paste NAT gateway. Since we need to place it in one of the public subnets, we can use subnet resource and its index. One of the biggest issues with this approach is that if you delete a subnet that is not the last one, Terraform will destroy all your subnets and recreate them. This approach is great when you need to create these resources once and keep everything as is. A more flexible approach is to use a map instead of the array. In this case, we can use a key to target specific resources. If we remove the first subnet, Terraform will only destroy that object and keep everything else in place. This is just one example. Let's copy and paste private subnets, and I'll show you this in practice. Once again, we need only a single resource. Let's update the variable to be more generic. You can add a subnet type, such as private or public, to the map itself and have a single AWS subnet resource for all your subnets. This time, we'll iterate over objects in the map using for each loop, gaining access to the key and value of the map. For the seeder, we'll use the value of the map and access seeder property of that object. We'll do the same for the availability zone using AZ property. Finally, we can update the name tag. The next step is to create a private route table. We can remove the second resource and, instead of using a count, iterate over the map as we did when creating the subnets. For the index, we can use the key of the map. This is why this approach is more flexible. We can target individual resources using the map's keys. Let's verify that everything is still working. You'll notice that when we apply Terraform, it uses map keys instead of array indices like 0, 1, etc. Alright, now we have private subnets. We also have private route table and a NAT gateway. Terraform has many built-in functions. For example, you can use seeder subnet function to dynamically divide your main VPC seeder. If you replace the values and apply, we should see no changes. Another common use case for the count is to use it as a conditional variable. Instead of creating array or map for the isolated subnets, let's create conditional variable to decide whether to create those subnets and set it to false for now. Let's copy and paste isolated subnets. This time we can use this boolean variable to decide whether to create isolated subnets. If it's set to false, the count equals 0, meaning no resources will be created. If it's true, the count is set to 1, and we create one instance of that resource. Since we have a false value, let's try to apply it. At this point, nothing will be created. If we want to create isolated subnets, we can set this variable to true and rerun Terraform. You'll notice from the output that when we use a count, Terraform uses index. The last thing I want to show you is how to dynamically create blocks within the Terraform resource. For example, some resources like a security group might have repeated blocks, such as ingress rules, that you need to copy and paste to open new ports. Let's go ahead and apply this for now. As you can see, we have a security group with 2 inbound rules. Now let's refactor it. Let's create another local variable with these rules, using a map with ports and keys as seeder ranges as values. Inside the security group, we can use a for each loop to create multiple blocks of the same type. If you apply this, you should see no changes since we dynamically generate the same 2 inbound rules. That's all for this tutorial. Next, we'll cover Terraform modules and best practices. You can find the full playlist in the description.